Okay, so this is the 5th lecture on advanced course in classical logic. And today we are discussing the problem how to recognize axiomatizations of the classical propositional logic. We already have one axiomatization. In fact, there are several axiomatization axiomatization in different textbooks. This is one of them. And so we have 11 axioms and the rule of modus ponens. We have 11 axiom schemata. These are not individual axioms, these are axiom schemata. And for this calculus, we know that a formula D is provable if and only if it is a tautology. So this set of 11 axioms axiomatizes the set of all tautologies, exactly the set of all tautologies. The question is if we are given other formulas, a finite number of formulas. So let us denote the previous formulas by B1, B11. And now we are given a finite number of arbitrary formulas. And we need to check algorithmically that this set of formulas, so we take these formulas as schemas, like in the previous slide. So these axioms with the rule of modus ponens and the rule of substitution. So if we consider them as schemas, then we can alternatively consider them as individual formulas, but we add the rule of substitution in our language, in our calculus. And the question is, can we decide if this set of formulas axiomatizes all tautologies, all valid formulas? More exactly, can we build an algorithm that checks this property? Intuitively, this algorithm will do two things. Firstly, it checks correctness, that we can derive only tautologies. And for this, it is necessary and sufficient to check that our formulas A1, AN are tautologies. If these formulas are tautologies, then everything that can be proved is a tautology. And if everything that can be proved is a tautology, then in particular, our formulas are tautologies. So this is an equivalent property. And this property, of course, is easily decidable. Well, not easily. We need exponentially many valuations. But still, it is a decidable problem. On the other hand, we need to check that this set of formulas allows us to derive all tautologies. So a completeness property, which means that for any formula D, if D is a valid formula, a tautology, then we can prove it from these axioms using modus ponens and substitution. So we take these formulas as schemata. And for this, of course, it is sufficient to derive our axioms A1, B1, B11. If we can derive them, then we can derive all tautologies. If we can derive all tautologies, then in particular, we can derive B1, B11. So this is an equivalent notion. But even for one particular axiom, say B1, it is not clear how to check this property. Formulas are A1, AN are arbitrary formulas. We don't even know that they prove any usual property of implication, conjunction, disjunction, and so on. And moreover, it was already shown in the science that there are finite collections of formulas A1 and such that if we take them as schemas and we use the rule modus ponens, then the set of derivable theorems is undecidable. So our difficulty was justified by the fact that there are undecidable calculi. And moreover, if there were no undecidable calculi, if we had only decidable calculi, then again we had a problem, because there is no guarantee that we have an algorithm that, given a finite set of formulas, builds an algorithm for this calculus, for checking that some formula is derivable from A1, AN. So there are two difficulties, in fact, in algorithmic checking a completeness property. Okay, moreover, there are strengthenings of this result. For example, let us remove conjunction and disjunction from our language. We have only implication and negation. It is a functionally complete set of connectives. And therefore, we can ask the following question: how can we axiomatize all tautologies that use only these two symbols? We already discussed this at the first lecture. The answer is that we can take the axioms for implication and for the negation, and these 5 axioms are sufficient to prove all tautologies. But again, we need to build a separate proof of this theorem. Well, this proof more or less goes the same way as the usual completeness proof. We build maximal consistent sets of formulas and so on. But we need to take some care about the fact that we don't have conjunction and disjunction in our language. We need to reformulate some definitions and proofs accordingly. We can even ask the same question for just implication. Of course, it is functionally incomplete. We cannot express all Boolean functions using implication. We cannot express, for example, the negation. But still we can ask the question, what if we want to axiomatize all tautologies that use only the implication symbol? Which axioms are sufficient for this? And surprisingly, the axioms for implication in our calculus from the first slide are not enough. We need also an additional tautology, Peirce's law. And then we can prove that a formula is provable from these 3 axioms or axiom schemata using modus ponens, if and only if it is a tautology for any formula that uses only implication symbol. Here we have 3 axioms. One could ask, can we do the same with just one axiom? Yes, we can. Such an axiom was found. There are, in fact, many axioms such that every of them is sufficient to prove all tautologies. And this is the smallest, the shortest axiom. And even there are many axioms of the same length that have the same property. So one axiom axiomatizes all tautologies. And there are, of course, axioms. There is just one axiom in this language, or in this language, or in this, even in this language, that is sufficient to axiomatize all tautologies in the corresponding language. All these axioms are already found, and there are even many axioms of this kind. And people investigated which axioms are the shortest ones, and so on. There is a big activity in this field. And I already mentioned this guy, Ted Ulrich, who collected many shortest axioms for various calculi for implication and negation, for equivalence. For equivalence, of course, we need some special rule of inference. We don't have modus ponens. We need a special rule. So this is a web page where you can find many these interesting axioms. So we mentioned already that some calculi are are undecidable, let us briefly recall what does it mean, and briefly recall some basic things that we know about decidable and semi-decidable calculi. So if we have some set, some universe, for simplicity, we can assume that it is either the set of natural numbers or the set of all finite words, finite sequences of symbols over some finite alphabet sigma. Then a subset of U is called decidable or recursive. In the following literature, they usually say recursive. If the following characteristic function of this set D is computable, this function takes an arbitrary word, for example, word or any element of U, and returns 1 if X belongs to D and 0 if X doesn't belong to D. So this function is from the set U. From the set U to the set 0 and 1, or to the set of natural numbers, for example. It doesn't matter. A set D is called semi-decidable or recursively enumerable, an abbreviation RE in the foreign literature, if the following semi-characteristic function is computable. So this function takes an input and returns 1 if this if this input belongs to our set D, and the function is undefined if the input doesn't belong to D. For the algorithm, this means that our algorithm stops in finite number of steps and returns 1 if X belongs to D. And this algorithm works infinitely long. So it makes infinitely many steps. It works infinitely infinitely long time. If X that doesn't belong to D. So of course we know many examples of decidable and semi-decidable sets. For example, the set of prime numbers is of course decidable. In logic, the set of all tautologies is decidable. The set of satisfiable formulas is decidable, of course. The following set of natural numbers. The set of natural numbers that are representable in the following form. So where A, B, and C are natural numbers. Directly from this definition, we can only say that this is a semi-decidable set. If we have an input number n, we can simply check all possible natural numbers A, B, and C and calculate this expression. If we obtain exactly n, then we stop and say yes, or say 1. But if we do not find A, B, C such that this expression is n, then we can't stop and we will compute infinitely long. So this set is, of course, semi-decidable. Is it decidable or not? It is not clear. So perhaps number theorists can prove that this is decidable set, perhaps not. If we put here some arbitrary expression, it is not quite clear. So in general, it will be semi-decidable. And only some of them will be decidable. Now, we are talking about calculi. So what is a calculus, a propositional calculus? So we are talking about propositional formulas built using an infinite set of variables, P0, P1, P2, and so on, using some connectives. For example, connectives, conjunction, disjunction, implication, and negation. But we can consider, of course, any other connectives. And by a calculus, we mean a pair that consists of two things: a set of axioms, which are just a set of formulas, and a set of rules. What is a rule? Usually rules have premises. For example, modus ponens has two premises, A and A implies B. And the rule with n premises in general is a relation between n tuples of formulas and formulas. So modus ponens is a relation between pairs of formulas and formulas. Moreover, this relation is usually functional, but only partial functional. For example, modus ponens is it is a partial function. It takes two formulas and produces a new formula C, but it produces a formula only if the second formula, so if the first formula is A, then the second formula must be of the form A implies some B. And only for these formulas it produces the result, namely B. If the premises are not of this form, then it doesn't produce anything. And usually this rule, the relation, is a computable function. Well, in the usual calculi, it is a simple, of course, this function is easily computable. Modus ponens is very easily computable. But in general, a rule is a computable partial function. And moreover, sometimes, so usually in the logics that we have in practice, a rule is generated by some formulae. So it is obtained by some substitution instances of some formulae. But now we don't need this more special case. So a rule is just any relation, any partial computable function between n formulas and formulas. And now a calculus will be called decidable or semi-decidable if the set of theorems or provable formulas of this calculus is decidable or semi-decidable. So what is a theorem? It is a formula that has a proof. A proof is a finite sequence of formulas such that each formula in this sequence is either an axiom or is obtained by some rule from previous formulas, so like in the usual logic. But later we will only consider calculi that have the set of rules only modus ponens and substitution. But let us first make some general statements, general observations. A first simple theorem. If we have a calculus with a finite set of axioms and a finite set of rules, then it is semi-decidable. So as we said at the beginning, so the classical propositional calculus is an exception. It is decidable. And the intuitionistic propositional calculus is decidable. But in general, if we have only finitely many axioms and the rules, even the rules of modus ponens substitution, then in general, we only obtain semi-decidable sets of theorems. Well, this is easier. So if we have an input formula D, how can we check that D is a theorem? We can simply build proofs one by one, proofs with length 1, proofs with length 2, and so on until we obtain our formula D. If we obtain our formula D, then we stop and say yes. If we didn't obtain our formula D, we simply build proofs again and again and again. So the process will be infinite. So in general, we obtain only semi-decidable sets of theorems. Moreover, this theorem can be strengthened. Here, finite can be replaced by decidable sets of axioms. Of course, every finite set is a decidable set. But of course, there are decidable sets of formulas that are not finite. For example, the set of tautologies is decidable but not finite. If we look at our calculus on the previous slide, on the first slide, we have 11 axiom schematas. And the set of all substitution instances of these 11 schemas is a decidable set. So given a formula, one can easily check that this formula has the form B1, has the form B2, or has the form B11. It is a simple algorithm. So this will be a calculus with a decidable set of axioms and the rule of modus ponens, for example. So this is an example of a calculus for Theorem 2. And in fact, the proof is the same. We build all possible proofs one by one. We simply build all possible sequences of formulas, and for each sequence, we check, is it a proof or not? And this is a decidable property, because for each formula, we need to check, is it an axiom? It is a decidable property. Is it obtained by from some previous axioms using some rule? This is a decidable property. Simply check all previous formulas and apply all possible rules. This application of rules is a computable process. So the proof will be the same. Again, we search for D. And moreover, we can even strengthen this Theorem 2 even more. We can replace decidable by semi-decidable sets of axioms and still obtain semi-decidable sets of theorems. So this is Theorem 3 again, copied here. So how can we do now? We cannot simply build all possible sequences, finite sequences of formulas, and check whether these sequences are proofs, because we cannot check in a finite number of steps whether a given formula is an axiom. But since our set of axioms is semi-decidable, in the theory of algorithms, there is a theorem. So every semi-decidable set can be represented in a computable enumeration. So there is a computable function, total function, from natural numbers to formulas. So A0 is a f of 0. A1 is f of 1. So we have a computable function from natural numbers to formulas, such that the set of formulas that it returns is exactly our set, semi-decidable set. And now we can use this enumeration to build all proofs. So for every number n, we firstly build all formulas a1, an, and stop here, and build all possible proofs of length at most n from these formulas using our rules, only from these formulas. Of course, if the formula is provable, it is provable from some finite number of our axioms. So at some number n, we will obtain the axioms that are enough to prove our formula D. And n will be sufficiently large so that the proof of length n will indeed prove our formula B. So we build all these possible proofs and check, did we obtain the formula D? If yes, we stop and say yes or return 1. If no, then we go to the next n. I'll leave the following question to you to think about. So in Theorem 2, we had decidable sets of axioms. In Theorem 3, we had semi-decidable sets of axioms. And in both cases, we obtained the set of theorems semi-decidable. Are these two kinds of calculi the same? Namely, if we have some calculus with a semi-decidable set of axioms, can we transform it into another calculus that has a decidable set of axioms and the same set of theorems? So I will leave this question to listeners to think. So can we transform a calculus with a semi-decidable set of axioms into a calculus with a decidable set of axioms and with the same set of theorems? So in general, calculi have semi-decidable set of axioms, set of theorems, and only some calculi have decidable set of axioms. Now let us return to our first question. Let us formulate it precisely. So assume that we have a finite set of tautologies. We can already think that they are already tautologies because this property is easy to check. It is a decidable problem. And we have two fixed rules, modus ponens and substitution. And we ask the following question: does there exist an algorithm such that its input is the set of this finite set of formulas, and this algorithm must always stop on any input a1, an, and it must return either yes or no, and it must return yes if and only if all tautologies can be proved from these axioms using these two rules. So a1, an are individual axioms, and we have this rule of inference to obtain a schema from an axiom. So we can substitute any formulas for any variables p1, pn. So the result by Linial and Post is that there is no such an algorithm. So no algorithm exists. So in particular, if we want to obtain another axiomatization of classical propositional logic, perhaps with some nice properties, for example, with one formula or with some formulas that have some nice property, then every time, in order to build the proof that this new axiom system is complete, we need to invent something. It is not an automatic procedure. So every completeness proof is needs some invention. So in other words, this problem is undecidable. And what are the methods for proving undecidability? Of course, in the theory of algorithms, there are many problems about Turing machines or about natural numbers, about words, and so on, that are already known to be undecidable. And here we have a problem about formulas, finite sets of formulas. The usual method of proving theorems like this is to make a reduction from some undecidable problem, for some problem for which it is known that it is undecidable, to our problem. So let us briefly recall what is a reduction. What does it mean to reduce one problem to another problem? We will reduce problems. What is a problem? Well, in fact, problems can be identified with languages. So if we have some finite alphabet sigma, sigma star is the set of all words, And a language is any set of words, possibly infinite set of words. And any problem can be represented as a language in some alphabet. For example, the set of prime numbers, the problem of checking whether a number is a prime number. It can be represented as a set of words, namely the decimal representations of numbers that are prime numbers. So sigma will be the set of digits, 0, 1, and so on, 9. And L consists of all strings that represent numbers in decimal notation, such that these numbers are prime. And similarly, for a tautology, we need sigma, some alphabet in which we can write formulas. And the language will consist of all strings that represent formulas that are tautologies. So problems can be identified with some languages. Therefore, we will introduce the notion one language is reduced to another language, or we will say one problem is reduced to another problem. We will call these languages as problems. So an algorithmic or an effective reduction of one problem to another problem. We use this symbol. So one problem, L1, in some one alphabet, is reducible to another problem, possibly in a different alphabet. The alphabets are need not need to be the same. If there is a computable function from one word to another word, from words in sigma 1 to words in sigma 2. So it transforms words in this language into words in this language, in this alphabet, such that for any word in the first language, it belongs to the problem L1 if and only if its image belongs to the problem L2. So if and only if. So a computable means that there is a, for example, Turing machine or a program in some programming language that computes this function. So f of x is computed in a finite number of steps for any x. So not only for x from L1, this function stops in finite number of steps, but for any word, this function must stop in a finite number of steps. But its result belongs to the second language if and only if its argument was in the first language. And this notion of reduction is closely related to the decidability and undecidability. So if we reduced the language L to L prime, and the second language is decidable, then the first language is decidable too. And by contraposition, if the first is undecidable, then the second language is undecidable. And of course, this is a almost trivial statement. We prove only A. So assume that L prime is decidable. So there is a Turing machine or program in some language, some computable programming language, such that for any input y, this Turing machine, for example, stops and returns 1 if and only if this input belongs to L prime. Now, how can we check using this Turing machine and this computable reduction function f? How can we check that some x belongs to L? Well, we firstly compute f of x. This is done in finite number of steps. And then apply this machine M prime. This composite process will be denoted by M of x. And this Turing machine or this algorithm indeed decides that x belongs to L. So reduction is the method of proving, for example, if we use line B, if we already know that some problem is undecidable and we reduce this problem to L prime, then we automatically obtain that L prime is also undecidable. Okay. Now, how do we prove undecidability of our problem? How do we prove lineal and post theorem? It will be only the brief sketch, only the idea. We will consider undecidable problem for the so-called tag systems, or they are also known as uniform post-production systems. There are also non-uniform post-production systems, simply post-production systems. But even for uniform post-production systems, the problem is undecidable. And of course, uniform things are easier to understand. So a uniform post-production system, or in other terminology, a tag system, is a triple. It consists of a finite alphabet. We need some order of letters. So we didn't say set, but we say an ordered m tuple. Technically, we need this. And we have m words. So x1, xm are just some words over alphabet sigma. So we have a correspondence between a1 and the word x1, am and the word x1. So we have m letters and we have m words in the alphabet sigma. And the last component, L, is just a positive integer. How can we apply this system pi to a word? If a word W has length at least L, then we say that our system pi is applicable to it. If it is a shorter word, then our system is not applicable to this word. The system pi stops on this word. So if it is applicable, if the length of W is at least L, then we apply pi to this word W as follows. So W has the following form: AI, some letter AI, then some word Z, then some word V, such that this first prefix AI and Z has the length exactly L. We simply delete this prefix AIZ and then put the word XI to the end. So, so we first look at our word W and remember this first symbol. What is the first symbol of our word? Okay, it is a symbol number I. Then we simply remove the first L symbols from W. Recall that our word has at least L symbols. Remove the first exactly L symbols. And then write the word XI to the end, not to the beginning, but to the end. That's it. A very simple transformation of words. And so one would expect that these systems are very easy. So if you have this tag system and you have some word W, you can easily start to transform it. So you start with some word W, you transform it once, twice, and so on, until so maybe this process will be infinite. You will always obtain a word at least L with at least L symbols, or perhaps at some point you will obtain a short word with less than L symbols. If this happens, this system pi, this computation stops. Stops, or in the foreign literature, they write halts. So our system pi halts on an input word W if this process, so the word W is transformed into the word W0, W1, W2, and so on. If this process obtains some word U, which is short, which is less, whose length is less than L. So notice that if we have a word W, our process is deterministic. The first result, W1, W0, is unique. And the second is unique, so we simply transform this word step by step until we obtain a word of length less than L. For some words W, there will be the stopping point. For other words, the process will be infinite. So the pi halts on the input W if this process stops after a finite number of steps. And it may seem that these are very simple transformation systems, so that it will be quite easy to check whether our system stops on this particular word W. However, it turns out that it is impossible to check this problem given a tag system and given a word. So the input of our algorithm has two things: a tag system and a word. And our algorithm must check whether pi stops or halts. I should write halt here. Halt on word W. And there is no such an algorithm, so we cannot check whether pi halts on W. So this problem is undecidable. Moreover, there is just one fixed tag system, pi 0, such that even for this system, this problem, our input will be just one word W, and we need to check whether this system pi 0 stops on this W. Even this problem is undecidable. There are several systems like this in literature, and they are not very difficult, not very hard. These words x1, xm are of length 3, 4, and so on. So just small words, and m is about 10, L is about 2 or 3, I don't remember. So you don't need to have a very, very big system. So even for not very big systems, this problem is undecidable. And we will use this undecidable problem to prove that our problem for propositional calculus undecidable. So here is again the formulation of the theorem. So there is no algorithm that checks whether a given set of formulas axiomatizes all tautologies. So our first problem is about words in some alphabet, and our second problem is about formulas. So we need to encode symbols or letters in the alphabet sigma with some formulas. This is done approximately as follows. We encode symbols A1, A2, A3 by formulas, by very easy formulas. For example, A3 will be represented as the formula. You have P, P, P here 3 times, and then P implies P. This will be the same in all formulas. So 3 indicates how many P variables P are here. So to every symbol, we assign some formula. Moreover, it is even a tautology. If we have a finite word, for example, like this, A2, A5, A3, A1, we encode this word into the following conjunction. So we put these formulas, put conjunction, and put a parenthesis to the right for uniqueness. And then we will, we need only to represent our tag system. So these words x1, xm, and these transformation rules into axioms. And we will have axioms that say approximately like this. If we have a word starting with L symbols, in which the first symbol is the symbol number I, then we have implication in our formula, and then some formula with this result. But V here is an arbitrary formula. We can't write infinitely many formulas for every V. But we use the propositional variable P here, or Q. And in propositional calculus, it is a trick. This trick helps you to represent all these transformations. If you write here, instead of V, just one propositional variable Q. And we have some, we will need some additional specific axioms that allows us to work with these long conjunctions. But anyway, for a proof for a post system pi and the starting word W, we will build a finite number of formulas, A1, AN. So our transformation rules will be represented as A1, A2, A3, and so on. And we will need some 2 or 3 specific axioms at the very end. And the rules, of course, are modus ponens and substitution. And this calculus will have the following property. If our system pi stops or halts on W, so this happens if and only if from our calculus we can prove all tautologies. So this calculus will have the property. So if we obtained some word of length less than L, then we obtain B1, B11. So our axioms of the usual classical propositional calculus, and of course, then all tautologies. If we cannot obtain a word of less than L, then we never derive B1, B11, and therefore we do not prove all tautologies. So this is just a basic idea. Therefore, this algorithm that transforms pi and W into this calculus is indeed a reduction from tag systems to our problem. Here it is incorrect statement. It is a reduction from the halting problem for tag systems to our problem formulated here. So the reduction is in the converse order. Okay, so this is the basic idea. Some more details are in the lecture notes, but all details can be checked in the corresponding papers, published papers. Moreover, so this was just a very old result. The complete proof was in 1964, but recently some more results were obtained. I will just only formulate them. It is not so what we already proved, that it is not possible to recognize whether a finite set of formulas axiomatizes all tautologies. So the class axiomatizes the classical propositional logic. Is it so specific to the classical propositional logic? What about intuitionistic logic? does the same theorem holds if we write here axiomatizes all intersignistic theorems? The answer is yes. For intersignistic logic, the same theorem holds. And now the question is, for which other logics the same question holds? And the answer is for all logics. So classical logic is not so specific to this. So if you have any system of axioms, so here we can have B1, B11, the classical logic, B1, B10, the intersignistic logic, or just any fixed set of formulas. We don't even need that they are tautologies. And we don't even need conjunction, disjunction, negation. We can only have just implication symbol in them. Then it is undecidable that a given, if we have some formulas A1, AN, we need to check whether we can prove these formulas. This problem is undecidable. So this calculus, the theorems of this calculus contain the theorems of the calculus D. So lineal and post theorem is not specific to the classical propositional logic. It holds for any logic at all. Well, in particular, if we just fixed one formula B, it is undecidable. The following problem is undecidable. If we are given A1, AN, can we derive this particular formula B? For example, P implies P, or for example, just P, or the first axiom of our classical calculus. P implies Q implies P. In all cases, it is not possible to check whether we can derive this formula from some given formulas A1, AN. Well, and the last result, if we have a calculus, so the last theorem holds not for all logics, but for all logics that can derive this first axiom of our system, P implies Q implies P. So if our logic can derive this formula, then it is undecidable that given us a finite set of formulas, whether this new calculus has exactly the same theorems as D. Here we had only inclusion, and here we have equality. So the difference is here. So at the very beginning, we discussed that the inclusion C implies D is not so obvious. It's not clear how to decide it. And in fact, it is not possible to decide it not only for classical logic, but for any logic. And the equality is not possible to decide for any logic that contains not all tautologies, but simply just one tautology. P implies Q implies P. So that's all for this lecture, and we can discuss questions.